John McGann. I'm a new employee at Exponent. Exponent is a scientific consulting company. My background is in polymers and advanced materials for alternative energies, and I'm in polymers and material sciences division within Exponent. And as Fred mentioned, I work for Haskell. He's my boss. So I'm excited to be here, and thank you for attending. So Exponent, as I mentioned, is a global multidisciplinary consulting firm, and we really cover solving important issues in science, engineering, and regulatory issues for a wide range of industries, whether it's civil and construction, environmental. I work in the engineering sciences, and we also work in technology development as well as transportation. So this talk is somewhat adapted from my work that I did at MIT, a technology that's called solar thermal fuels. And it's a research project still. It's still an academic research project, but there's a lot of interest in it now because it's a new thing that's, as I'll talk about, there's a lot of new hype around this technology. But there's a lot of overlap with the textile communities, in particular the material that is the core of this technology. And so I'll talk about first what a solar thermal fuel is, because no one really knows about it for good reason. Two, what azo molecules are and how it relates to this technology. And third, where solar thermal fuel research is and where it needs to go. And fourthly, some sort of ideas that, with the help of Sloan business students at MIT, how this technology could be implemented and where it could be implemented into the textile community and fabrics. So, solar thermal fuel is a material that does three things. One, it charges from the sun's energy. So it takes the energy from the sun and stores it, kind of like a solar cell, but it doesn't convert it to electricity. In this case, it takes the energy and stores it for a certain amount of time. It remains charged, and then when you need it to get the energy out, you trigger it somehow, and then the energy comes out as heat. So it's heat on demand that's optically charged, and it's completely cyclable. And so ideal properties of the solar thermal fuel is that it's a closed loop cycle, so there's no emissions, there's no additions to it, it's completely contained, there's negligible decay and recycling. One of the cool things about it is that as opposed to other solar thermal technologies, when it's stored and charged, it's actually charged at room temperature. So you don't have any problems with handling it. So it's on-demand usage. And lastly, depending on how you engineer the molecules, they could be a liquid or a film. And obviously for textiles, maybe one film. So when people typically talk about solar thermal, they typically talk about phase change materials. And for the textiles community, the fashion community, phase change waxes are really the comparison to this material. So just a quick chart kind of comparing the two about some of the unique aspects of what a solar thermal fuel is. They obviously both deliver heat. As I mentioned before, solar thermal fuels store their energy at room temperature as opposed to waxes which store their energy in the melt, so hot. The storage lifetimes are significantly different. Solar thermal fuels should be able to store their energy for days and possibly over a week. Solar thermal fuels are optically charged, so when you put it in the sun, it's charging, versus waxes, you need to actually supply heat to charge it up. Charging times are pretty comparable. Output temperatures, the output temperature of a wax is whatever the melting temperature of the wax is. Solar thermal fuels here, I'm writing less than 400 degrees Celsius, and that's really high, and there's this asterisk next to it, because these are computationally predicted values. We haven't gotten this in the academic setting, and I'll talk about why that is and where we are compared to that. But theoretically, we should be able to get pretty hot temperatures if you need them. And obviously for fabrics, you would never want to get that high. But and it has pretty comparable energy densities to that of phase change materials. And so, but the big difference is that solar thermal fuels are very much a research project at this point, with the hopes of commercialization at some point in the near future, whereas you can buy phase change materials at Yankee Candle. So azos and azobenzenes are the core technology to solar thermal fuel. And I'm sure many of you here are very familiar with azos. So azo is the core functional group that really does the magic in this whole thing. And that's this nitrogen-nitrogen double bond here. And I've highlighted in this red square the azo group in azobenzene. And for solar thermal fuels, azobenzene is the key molecule of interest to this technology. So azos And this azo group is found in azo dyes, and azo dyes are very important in the textile community. They account for approximately 70% of all the dyes used, and they're found in many different classes of dyes. And so I'm just showing two examples of some commonly sold dyes. And you can see I've highlighted these magic azo groups in here, so it's pervasive throughout all of this, that nitrogen doubling. And I'm sure many of you are aware that azo dyes are regulated pretty heavily, especially in Europe, because their byproducts from degradation are known to be carcinogenic. Specifically, the chemistry is that when they degrade into aromatic amines, those are the ones that typically cause problems with regulators. So everybody knows the color properties of azo dyes. One additional property of azos, specifically azobenzene, is that it can undergo what's called photoswitching. So these molecules have a certain shape. And if you shine the right wavelength upon it, some of these azos, specifically azobenzenes, change their shape when you shine the light. So one has this lower energy, and this is the typical shape or conformation of that molecule. If you shine the right wavelength on light, it will change its shape. And this new shape is higher energy. So there's an energy difference between your previous material and your charged molecule. And you can go back and forth, shining different wavelengths of light going between them, or another route is to charge with light and then supply some heat to just kind of trigger the back reaction, and then you get a lot of heat back out. And that's what the solar thermal field process is. I'll describe that more in detail in a second. Not many people know about this. It's definitely not found in azo dyes, so you don't have to worry about your azo dyes switching in fabrics. The energetics don't work out, that azo dyes just can't take these additional shapes. So that's something that you don't really need to consider for normal azo dyes. But for azobenzenes, this is a very common phenomenon. And people really like the use of azobenzenes because they really cycle very well and very rapidly without any degradation. The reason that people haven't used it so far for solar thermal fuels is the energy isn't high enough yet. You need to make the energy higher.
John, aren't the so-called photochromic dyes that we had a big splash from the Japanese 10 years or so ago, where you put your hand on your pants and it would grow the same type of cis-trans formation and produce a different color, and then as it cooled down, of course, it reverted back in that same type of concept?
It must be. I know what you're talking about. I don't know what the material is, but it's got to be similar to that.
Look at it.
Yeah, that. I forgot about those. Yeah. So people have used this photo switching for two different reasons. In research, people use them actually as actuators, so they take advantage of the fact that there's a real significant size change or length change between these two molecules. So if you make some sort of fabric or film coating these molecules and you shine light on one side of it, there's a pressure gradient that forms in the material, and you can cause it to bend, and people use this for actuators, and it's very cyclable and very triggerable and fast. So it's really cool technology. But for solar thermal fuels, it's a little different. As I mentioned before, these two molecules are different, or have a difference in energy. And what I'm showing here is an energy surface. So you can think of the y-axis as just energy, and really the difference between them is the energy stored, which is essentially the temperature that you get out. So the more energy you store, the higher the temperature of the material. And in its ground state, it wants to stay in this little valley here, and there's some barrier that it has to overcome to release the heat. And the height of that barrier is basically the storage lifetime of this material. And so when you trigger it, the way you get the energy out is that you give it a little boost. You supply a little bit of heat to get it over this barrier, and then you get all the energy back plus the additional stored energy in the system. So the cycle goes like this. So you start with your uncharged molecule, your transistomer. It absorbs light, goes to some higher energy surface state. It switches and stores its energy in the new conformation, and then when you need the energy later, you trigger it, and you get heat out. So that's the cycle. So what's holding this technology back? It seems like pretty straightforward. Why hasn't anybody been able to do anything with it? So it was actually researched pretty heavily in the 70s and 80s, but for a variety of reasons, they just couldn't get it to work. Whether it was some combination of low energy density, so low temperatures, degraded upon cycling, short storage lifetimes, or even it was way too expensive. And so there was a paper that was published in 1983 that basically said, although this technology is technically feasible, it's not economically justified at all. And so people gave up after this. They said, okay, this was a great attempt, and it kind of just went to the shelves of the academic libraries until now. And so what's changed? Since the 80s, we have really two things at our advantage that weren't available in the 80s. One is significant advancement in computational power. So we can try all new molecules that really you have to do brute force. Now you can do them with computers. Second is all sorts of new molecular engineering tools. Nanotechnology is a buzzword that people like to use, but there's all sorts of new things that people like to use. And so maybe you can combine these new strategies and come up with something that can actually work for solar fuels. So the work that was done in my research group at MIT, this was started in 2011, the idea was to take these azobenzenes and pack them on some sort of, what I'm calling a substrate. It's not your substrate, but chemist substrate. And you really force them to stack really close to one another. And I can talk later if anyone's really interested about what that does to the energies, but it basically increases the energy density of the system quite dramatically. And so this is all computationally predicted. So you could, azobenzene typically has 40 watt-hours per liter, but the theoretical mass is many-fold higher than that.
Is that a conductive substrate?
This one is not actually, because you actually when you functionalize these, you end up ruining the thermal conductivity of the material. But that's something that's also very interesting for this, designing that substrate for the right conditions for the thermal conductivity. It's a good question. So the energy densities at least are predicted to be able to be comparable to that of what you can get in commercial lithium-ion batteries. So pretty energy dense. So that was computational work that was done, and like you mentioned, this is a carbon nanotube that I'm showing here. That's where the project started. It doesn't have to end there. We've done more work showing that you can do many other types of substrates, as long as they meet the conditions where you pack these azobenzenes fit close to one another in a rigid way. So polymers are definitely in play here. And so that's where a lot of the work in my group that I'm no longer at is going. So we've experimentally proven that this approach generally works. Where we're at now is that the temperatures are still too low to do anything useful with, but there's research ongoing we think that we can get better and better with time. So that's where the research project is at this point. So when we think about including them into the textile community, there's several advantages that at least I thought there might be, as well as the Sloan business students that I worked with at MIT to kind of investigate this as a textile. One is that since it is an azo molecule, it has some of the same color changing properties that typical azo dyes are. So that's kind of a plus. Second, there's a lot of industry knowledge about how to process, store, and manufacture these dyes. So there's a lot of industry knowledge. You can potentially apply some of that knowledge to this technology. Additionally, similar to how phase change materials are incorporated into fabrics now, you could micro-encapsulate these solar thermal fuels if you wanted to in a liquid form. For branding purposes, you can think about it, you can potentially brand it as a green technology because it is a solar powered technology. And so that might be a plus. So the initial market that the Sloan business students thought of was outdoor sportswear. And, I'm drawing, the student drew these really great sketches. And this is obviously an exaggerated case where you're skiing, but if you've skied before, sometimes you get hot because your jacket's too bulky, or you fell in snow and now you're too cold, and it's tough to find that right balance. And so there's this cool skier going down the slopes there, and it gets a little cold, you press a button, and all of a sudden you get a little hot, a little heat in your jacket, and you feel better. That's kind of the concept of where they thought this technology could fit in. How you practically do that, that's a longer conversation, but that's kind of the idea. So the specs that they found very useful for the outdoor sportswear is, it would have these kind of properties. It would charge in the sun. It would take about an hour to charge. It would stay at room temperature while it's charging, and when it's stored, it can keep that energy stored for 10 or so days and release that heat on demand, a button on your sleeve or somewhere else, depending on where you needed it. And it would give off energy of about 100 Fahrenheit for about 10 minutes. That's kind of the gold standard of where they thought this technology should be for this work. But they didn't stop there. They thought, this is a great first market. They also thought, they can expand this into women's fashion too. There was a lot of interest in the fact that smart materials for women's fashion is becoming a thing. And so the idea for including solar thermal fuels in them was that for women or men who have light shirts on when they're going from the car to the dinner at nighttime in the cold environment, they don't want to put on the jackets, they want to look good still, whatever, they just press the button and they stay warm for that short period, that short walk to whatever event they're going to. So there is a decent market potential for this. These markets are relatively big, especially women's fashion, and some of them are growing. So they really thought maybe there was a significant opportunity if you can get it to where it needs to be, of course. So in conclusion, solar thermal fuels, I think, are an interesting alternative for a source of on-demand heat, specifically in the clothing world. The technology is still in the research and development stage. Hopefully that will come out in a couple of years. Maybe it will take longer. Who knows? That's what research is fundamentally. Material similarity to azo dyes might allow for easier manufacturing inclusion, and there are potentially market opportunities if the technology can meet the performance specifications and the cost requirements. So I'd like to just acknowledge and thank my MIT advisor, Professor Jeff Grossman. He's in the Material Science and Engineering department, as well as the 4 Sloan business students at MIT who helped flush out some of the ideas in the textile world and the market. Thank you.